The results reported by any software for a VECM model have three common elements: the cointegrating vector, the adjustment parameters, and the short-run coefficients. From the previous tutorials, you know that the cointegrating vector contains the long-run equilibrium relationship and the long-run coefficients. The adjustment parameters determine how fast the variables converge towards the long-run equilibrium to correct any short-run disequilibrium. The short-run coefficients are associated with the lags of the first differences and represent the short-run impact. In this illustration, we have presented the results of the restricted constant specification estimated using the R commands. Therefore, we have a constant in the cointegrating vector, but no constant or trend in the short-run part. For a better understanding, let us look at where these results fit into the VECM equation for restricted constant. We have used different colors in this visualization to show exactly where the coefficients and their variables belong. Here alpha, shown in red, is a 4×1 vector containing all the adjustment parameters from the four equations. The first element in this vector -0.213 is the adjustment parameter of the first equation of delta LRM. The second element 0.115 is the adjustment parameter for the second equation of delta LRY, and so on. The beta transpose, shown in dark green, is the cointegrating vector containing all the parameters of the long-run equilibrium relationship. The first element of this vector corresponds to LRM and has been restricted to 1. This is due to the Johansson normalization restriction, which imposes our square number of restrictions. With one cointegrating relationship, R is equal to 1 and R square is equal to 1. So, we only need to impose one restriction. The constant shown in gray belongs to the cointegrating relationship and is added to the cointegrating vector. If we had included a trend in the cointegrating relationship, it would also be specified here along with the constant. The matrix theta, shown in light blue, is a 4×4 matrix representing short-run coefficients associated with all the equations. These coefficients correspond to the first lag of differences of all the variables. In this matrix, the first row shows the coefficients of the first equation of delta LRM. The second row shows the coefficients from the second equation of delta LRY, and so on. Since we only have one lag of differences in our VECM, we only have one theta matrix. If we had two lags of differences, we would have to include theta 2, which would be another 4×4 matrix representing the coefficients of the second lag. Therefore, the number of theta matrices is equal to the number of lags in VECM. Shown in light green, the vectors ω1, ω2, and ω3 contain the coefficients associated with the centered seasonal indicators. The first element of these vectors belongs to the first equation of delta LRM, the second element belongs to the second equation of delta LRY, and so on. Considering all the equations, variables, and their coefficients, the VECM model in our example will look like this. This matrix form contains all the equations, adjustment parameters, cointegrating vector, short-run coefficients, and seasonal indicators. You will notice that delta yt, delta yt-1, and yt-1 are 4×1 vectors because we have 4 equations due to 4 variables. Let us move on to the interpretation of the VECM model. First, we will look at the cointegrating vector and the long-run equilibrium relationship. This part, including the beta coefficients, yt-1 and the constant, show the cointegrating or long-run relationship within the VECM equation. When this cointegrating part is equal to 0, the variables are in their long-run equilibrium. This implies that if this element is not 0, meaning it could be positive or negative, then we have disequilibrium in the short run. For long-run equilibrium, this element has to be equal to 0. To understand the long-run equilibrium relationship, we can write these coefficients and variables in the form of an equation. This equation will be equal to 0 at the equilibrium. We can keep the restricted variable LRM on the left-hand side and take all the other variables to the right-hand side of the equation. This gives us the long-run equilibrium relationship between all the variables. You will notice here that the coefficients have changed their signs when we represent them in this equation form. Hence, when interpreting the long-run cointegrating relationship, we have to reverse the signs of the coefficients in the cointegrating vector. This is simply because the cointegrating vector has to be normalized and is represented in a different manner in the VECM equation. Now, the interpretation of the long-run equilibrium relationship is straightforward. If we look at the coefficient of LRY or real income, we can observe that it is positive. This means that there is a direct and positive relationship between the demand for money shown by LRM and real income. If real income increases, demand for money will increase as well. This relationship, therefore, is exactly what we expected. When interpreting the coefficient, we have to be careful of any transformations that we applied to the variables. For instance, both real money and real income have been log transformed here, so the coefficient 1.033 can be interpreted in terms of elasticity. If real income increases by 1%, then demand for money will increase by approximately 1.033%. In the case of IBO or bond rate, the coefficient is negative. We see an inverse relationship here as expected. This implies that if the bond rate increases, then the demand for money will fall. This makes sense because if the bond rate is increasing, people would rather invest in bonds for more profit instead of holding money. As a result, the demand for money will decrease. Similarly, the relationship between IDE and demand for money is positive. The variable IDE is the bank deposit rate. Remember that the LRM variable follows the M2 definition of money, which includes the currency and the bank deposits. Therefore, we expect IDE or deposit rate to directly affect demand for money here. If the deposit rate increases, people will deposit more. Since deposits themselves are a part of the demand for money, LRM will also increase. Another important thing to note here is that this long-run equilibrium relationship will be stationary if the VECM is correctly specified. As we have included a constant in the cointegrating relationship, this equation has to be stationary around this constant. In the goodness of fit part, we will check whether this is stationary or not. We discussed that the cointegrating part is equal to 0 at equilibrium. When it's 0, the variables are at their long-run equilibrium. However, the variables don't always stay at their long-run equilibrium. We observe disequilibrium in the short run when this element is non-zero, that is, it is either positive or negative. The more positive or more negative the value, the bigger the disequilibrium. We can also see this disequilibrium as an error in the long-run equilibrium relationship. The correction of this disequilibrium and convergence back to long-run equilibrium depends on the sign and value of the adjustment parameters in alpha. First, let us see whether the adjustment parameters have correct signs or not. In Tutorial 3, we discussed the condition for determining the correct sign of adjustment parameters. According to that condition, the product of the adjustment parameter and the corresponding coefficient in the cointegrating vector must be negative. The first adjustment parameter of -0.213 belongs in the first equation for delta LRM. Because it belongs to delta LRM equation, we have to consider the coefficient of LRM in the cointegrating vector. You will see that LRM has been restricted to 1 in the cointegrating vector, so the adjustment parameter has to be negative to achieve convergence. In our example, the first adjustment parameter has the correct sign. For any coefficient that has been restricted to 1, the adjustment parameter must be negative. Similarly, the second adjustment parameter belongs to the equation of delta LRY. This adjustment parameter must be positive because the coefficient of LRY in the cointegrating vector is negative. We can see the same situation in the case of the fourth adjustment parameter and IDE. So, the first, second and fourth adjustment parameters have correct signs. However, the third adjustment parameter in the equation for delta IBO is positive. Furthermore, the coefficient of IBO in the cointegrating vector is positive as well. This means that their product will not be negative and it violates the convergence condition. Still, we don't need to worry here because this adjustment parameter is in fact statistically insignificant. So, the variable IBO will not diverge. The other adjustment coefficients are significant. We can see 3 stars next to the first one, meaning it is significant at 1% level. The second and fourth are significant at 10% level. Hence, the signs of the parameters fulfill the condition for convergence. In tutorial 3, we also discussed about the value or magnitude of adjustment coefficients. Ideally, we want the adjustment coefficients to be somewhere between 0 and 1 in magnitude. This ensures convergence back to long-run equilibrium. If the magnitude of these coefficients is between 1 and 2, it leads to oscillatory convergence behavior. On the other hand, if the magnitude is greater than 2, then the variables will diverge and the long-run relationship breaks down. In our example, you will observe that all of our adjustment parameters lie between 0 and 1 in magnitude, which is a good sign. When we look at the first adjustment parameter for LRM, its magnitude is 0.213 and its sign is correct as well. This means that 21.3% of the disequilibrium will be corrected in the next time period. For instance, if LRM is above its long-run equilibrium by 100 units, then it will converge back to equilibrium by 21.3 units in the next time period. Similarly, the adjustment parameter for LRY is 0.115, meaning that 11.5% of the disequilibrium in LRY will be corrected in the next time period. The adjustment parameters for IDE and IBO are very small. The variable IDE has an adjustment parameter of 0.029, which shows just a 2.9% convergence back to equilibrium in the next time period. On the other hand, IBO will not converge at all because its adjustment parameter is insignificant. So, what will happen in such a case? Will the variables converge or not? This gives us very interesting results to interpret. Here, we have a combination of variables that lead and others that follow. Consider LRM and IBO for example. IBO is a leading variable here and LRM is the one that follows. We say this because IBO does not converge, rather LRM follows it because LRM will converge to the long-run equilibrium. Let us demonstrate this behavior from a policy analysis point of view. Suppose we want to raise the demand for money in the economy and increase LRM. To accomplish that, we can try to directly deliver a positive shock to LRM to raise its value above equilibrium. But that will not work because LRM will simply converge back to equilibrium over time and the increase will just be temporary. From the long-run relationship, we know that IBO and LRM are inversely related. This means that we can increase LRM by reducing IBO. So, we deliver a negative shock to IBO to reduce IBO and increase LRM's value. Remember that the adjustment parameter for IBO is insignificant, so it will not converge back to equilibrium. Instead, the LRM variable will adjust and increase to restore the long-run relationship. This happens because LRM has a significant adjustment parameter, while IBO does not. So we can accomplish the increase in LRM by reducing IBO because IBO is the leading variable and LRM is the follower. We used this illustration to demonstrate how different coefficients can have deeper meanings in VECM. Here, we saw a situation where equilibrium will be restored in a unique manner and how we can view these relationships from the policy point of view. Now, let us look at how the variables will change in the short run. Here, we will consider the short-run part or first differences and observe how the short-run adjustments will occur. For illustration, let us assume that there is disequilibrium in the short run and the component shown here is positive by 50 units. We can also represent this in the equation form and it will show up as a positive error of 50 units. Due to this shock, there is a deviation of 50 units from the long-run equilibrium relationship. This deviation could be negative as well, but we are considering a positive deviation as an example. Since we are considering a positive error or shock, the variable LRM will be above its equilibrium value by 50 units. This is because the error will be added to this long-run equilibrium relationship, thereby increasing LRM by 50. Hence, in the short run, variable LRM is above its equilibrium. To converge towards equilibrium, we want this variable LRM to decrease in the next period. This also means that we want delta LRM to be negative because it represents a change in LRM. We want the change in LRM to be negative so that LRM will decrease. This is exactly what will happen based on the coefficients we obtained. Due to a positive error of 50, cointegrating part will be positive. We know that the adjustment parameter alpha1 for LRM equation was minus 0.213. Therefore, this component will end up being negative for LRM equation. Other things remaining the same, this will lead to a negative delta LRM and LRM will decrease by 10.65 units in the next period. This is exactly what we want for convergence. Similarly, we can consider the second equation for LRY as well. We know that LRM is above its equilibrium by 50. At the same time, this also means that the variable LRY is below its equilibrium value because the two are positively related. LRY has to be much higher, approximately 48.4 units higher, in order for LRM to be 50 units higher. Only then these variables will be in equilibrium. Therefore, to converge towards their long-run equilibrium, LRM has to fall and LRY has to increase. So, we also want delta LRY to be positive. This is exactly what will happen because the adjustment parameter alpha2 for LRY is positive at 0.115. So, this entire component will be positive, delta LRY will be positive and LRY will increase by 5.75 units in the next period. This same logic can be extended to IBO and IDE variables. The variable IBO is above its equilibrium value because we know that IBO and LRM are inversely related. For LRM to be higher by 50, IBO has to be much lower, approximately 9.6 units lower, as they are inversely related. This means that IBO is above its equilibrium, just as LRM is above its long-run equilibrium. Therefore, even though IBO won't converge, LRM will decrease and converge towards equilibrium as we observed earlier. The variable IDE, on the other hand, is below its equilibrium value and we want it to increase in the short run. IDE will increase by approximately 1.45 units in the next period. Therefore, the adjustment parameters and cointegrating relationships observed here are exactly as we expected based on theory. Apart from this, the short-run coefficients and variables can also play a role in determining the short-run changes. In the first equation for delta LRM, we can see that none of the coefficients is statistically significant. In the short run, changes in other variables do not seem to have any significant effect on the demand for money. In equation 2 for delta LRY, we can see that the coefficient of delta LRM is significant and positive. This implies that an increase in demand for money from the previous period leads to an increase in real income in the current period. The other short-run coefficients and their effects can also be understood in a similar manner. Thank you for watching and I will see you in the next tutorial.